Welcome everyone. My name is Adam Hall. I'm here today with Tom and Will, and we're going to talk to you about Opus and PryVote and the brave new world of self-sovereign identity. So we're going to quickly go through centralized trust, why that's a problem, and we're going to go into self-sovereign identity and what that is and how you can begin to build with some of the tools that we've developed. And we're also going to go into Opus and PryVote, our two flagship SSI projects. So first off, how is trust resolved when browsing the internet? So when somebody wants to host some web platform, some service, they will have a public key and a private key, which they will send in the form of a certificate signing request to a certificate authority. The certificate authority will then sign that with their private key and then return that as a signed certificate so that the third party can present their public key to anyone that would then interact with them. And that public key has been verified by the certificate authority. And then what this allows is this third party or any other service provider online can serve HTTP with the certificate, and it can be encrypted with their private key, and then the user or the client of the user can decrypt that with the public key of the third party. And this means they know that that came from that third party. And this also means that they can send their user data to the third party to be stored on their databases and for this to be encrypted and sort of confidential while in transit. So why is this a problem? Well, actually, once the data has left the hands of Alice, Bob, and Carol, they don't have much control over what's then done with it. They're sort of at this, the mercy of the information security policies of this third party, whoever they may be, and they just have to sort of hope that nothing gets stolen by a data thief. And this is quite actually a ubiquitous problem in today's climate, where, let's say, Marriott lost 500 million user records, I think, between 2012 and 2018. It might also get subpoenaed by the government, and this might not be a problem in a lot of places, but if you're an illegal asylum seeker in America, or a Rohingyan in Myanmar, or an Uyghur or in China, then this can be a life or death situation. And it also could just get bought by some other third party who's interested in doing some data science or whatever else on this data. And whatever happens, Alice, Bob, and Carol, after they send their data in this stage, they're no longer attached to the mechanism. So how did it get so bad? So to tell this story, we need to sort of look at really just the history of the internet. And that begins in 1990 with, well, it doesn't begin in 1990, but Web 1.0 begins in 1990 with the Web of Documents. And this is just static HTML, which is served by service provider, maybe selling books, and that's how Amazon started, or just sending emails or whatever else. At this stage, only 16 million users are on the internet. And the sort of things that they're doing on the internet are browsing these static HTML pages, or maybe they're going to send an email to their one other friend who has a Nokia 9000 and is able to actually send emails on the go. So, and as people started to be able to host just static files, people were able to then host bootlegged files. Google sort of came about, and this HTTPS protocol was, the RFC was specified in, I think it was 1999. During this time, the EU created the Data Protection Directive, and this was aimed to legislate against the misuse of people's information online. And what they were sort of targeting was the websites of these times, these just, non-reactive sites. And also, I suppose, like the Napsters of the world. The problem with the Data Protection Directive is that since if I'm going to be doing something which is in contravention with it, if I just go to some external country with more lax rules, then I can just do that processing over there and not be held under that jurisdiction. So in 2000, when the social web began to emerge, the international safe harbor privacy principles came about. And what these would do is these would hold anybody who is processing data about an EU citizen elsewhere accountable to the rules outlined in the Data Protection Directive. But already the internet had changed quite a lot to like this age of like Facebook, Xbox Live, online gaming, from this world of just static web pages. But largely, this is the Data Protection Directive is what was the backbone of what was being used to protect our rights in this world. And then, yeah, we began to see this this social web where you can begin to upload things about yourself onto these service providers' websites, and you can start gaming. We saw viral videos begin to emerge. iPhone was invented. World of Warcraft had its world's biggest beer fest, held in the Guinness Book of Records. Had some trolling, and which sort of grew into sort of online bullying. I don't know if anyone remembers Sarah Black Friday, which went viral, and she, I think, subpoenaed the production company to then take it down. And this is just generally going through this progression of getting, there's more and more services online about us, and it's still not really been regulated since 1995, or I suppose 2000, but this is relatively lax regulation still. And I'm not saying that there hasn't been regulations that have been introduced since International Safe Harbor privacy principles by other independent countries, but they won't all have been they won't all be as well thought out as let's say GDPR or something like that, and they rarely are they. So things, the big data revolution began in around 2010, and Facebook began to create sort of ads optimization / conversion software. So in connection with Facebook Business and Google, like Google Ad like software, they Cambridge Analytica were able to use this information to create sensationalist disinformation to target a bunch of different voters in the Trump election. And what they're able to do was get the users to start with signing a form, and then this would give you access to their friends' data, and these they would be taking some personality test, and these data points were correlated with external data points to create this really information-laden data set on these voters, 2 billion people in 11 key states. And this is started by Cambridge Analytica, and there's a ton of examples of this happening in sort of Western democracies where things are getting dishonest, indecent, and untruthful, downright like divisive. But it's not just happened in these countries. It's happened in over 100 different elections in 30 different countries. One of which, is the UK during Brexit. So Cambridge Analytica scandal came in around 2018, and like sort of alongside GDPR, and GDPR has sort of been tasked with now legislating against what the last like 20 years, 15 years of progress in this technological space, where things have developed to like an unrecognizable state. And in a lot of ways, the horse is bolted, because even after GDPR was put into action in 2018, in 2019, still 25 EU member states are still tracking users on their websites. And things just seem to be getting crazier and crazier. And disinformation seems to be so rife that we can see the world burning in front of us, but still there's not enough of a majority to make decisions which can take us into the right direction, because there's such a massive targeting of disinformation and sensationalist information. So none of this could really happen in a decentralized infrastructure where users control their own data and they control what processes get run on their systems. So we've begun to build a bit of a step in the right direction to decentralize this. And I'm going to hand over to Will to give a bit of an introduction into self-sovereign identity and what can be sort of done with it. Okay, cheers.
I'll go pretty fast because I want to get onto the code. I think hopefully that's what people want to see. So yeah, I mean, while that evolution of the internet was going on, there's also this evolution of digital identity systems to go alongside that. As we move to the social web, people are uploading information, sending information. There needs to be some way to correlate who are these digital identifiers, who do they actually represent in the real world. And there was several iterations on this. The first is, everybody just says, oh, I'll create a username and password system and I'll store their information in my service. Obviously, then you have loads of username and passwords. It's not very secure. Everyone has to implement that themselves. They all do it a different way. Have a little bit of a mess. And then there's the federated system, which is better, but then you have these entities like Facebook who become, these service providers for many websites and are able to sit in the middle of all of your digital interactions. And so, the next iteration, and I think it's worth pointing out, this is an iteration. There's not the, I don't think we're going to solve this, but it's called self-sovereign. And it's about, how do we enable individuals or basically any entities to interact with the same capabilities in the digital space, the virtual space. So yeah, quickly, I mean, these two slides, so I know Christopher would say these were principles and laws of self-sovereign identity, kind of like the laws Kim Cameron put out. And they're, I guess, they're old now and definitely open for challenge, but they're kind of things that we're aspiring to create in our digital systems. So like consent, access, making sure there's transparency, portability of information. So a lot of the same things GDPR is kind of advocating for is really some things that some of the ideology we're trying to get for in self-sovereign identity. And then this is a great slide. There's a really good presentation here that I would definitely recommend checking out. It's kind of the things that we're trying to enable with this new technology. So like our old systems, to start with, they're not going to scale to like the Internet of Things. We can't keep having a few service providers managing many people's accounts. Like, it's just not it's not kind of the future we want to enable. It's going to start limiting us. So I think this is good just to kind of point out what we hope to sort of start to enable with this new technology. Yeah, and so for me, I think this is important. Like, we want to empower entities, being individuals or any other entity, to actively participate in the digital interactions and relationships. They're not ever going to be the sole, in a relationship is not just you, right? There's two people at least. And so it's a negotiation, and we want to provide the tools that's going to enable people to start, having a seat at that table. Whereas at the moment, we don't have a seat. If we have to access these services, we kind of, we tick all the boxes, we fill in the forms, we give them the information, and then it's kind of, oh, let's just let someone else kind of manage that for us. So quickly, the technology so far. So for me, this originates in cryptography. Some people maybe say differently, but the cryptography goes back a lot further than the digital identity stuff. We're talking back in 1985, security with identification. Definitely recommend checking out that paper if you've not read it. It gives you a really good background of like the thinking. A lot of the problems that Adam outlined there were touched on in this paper. And then it's really this battle of how do we get this cryptography, which is getting really powerful, really advanced, into a world where we can start leveraging that as individuals, organizations, and people. And how do we do it in an open way so that it's not just closed source systems, but everybody can play together, and build things that work together. So here are a few standards that are kind of being incubated, almost incubated, in progress. Yeah, and then there's this trust triangle, which is kind of, the model. I don't know, some of you probably know it already. It's basically, an issuer has some information stored on a distributed ledger, uses that information, in particular a public key. So they have a private key, which they sign a credential, a data blob about a holder. They give that data blob to the holder. The holder then can create a cryptographic presentation, which they present to the verifier. And the verifier can read from this distributed ledger to check the public key and make sure that the integrity of the information is correct. And then you have this question about provenance, which is, how does the verifier knows the information hasn't been tampered with, but how do they trust the issuer? And that kind of goes back to the certificate authorities stuff, but instead of there being a few certificate authorities, now we get to, build our domain specific certificate authorities, and the verifier can choose, which kind of entities do they trust for their context to make statements which are going to be meaningful for them. Yeah, and I guess, again, these are peer-to-peer relationships that are separate, right? Like the holder is the only entity in both of these relationships, right? There's no correlation possible, or we want to avoid correlation between these different relationships that the holder might engage in. So really quickly, I just want to go through Vidcon, because I think this is a really powerful tool that's kind of below like the verifiable credential stack, but it's more about, how do we enable two parties to exchange information so that they can communicate as peers, right? They can communicate anything. They can send messages, they can send, they can prove credentials about themselves, but really they can start to build this relationship as equal parties to the relationship. And essentially it's, we exchange, so I exchange a DID document, which contains something called like an endpoint, like here's how you send messages to me, here's my message block, and here's my padlock. If you lock your message with this padlock, put it in my message box, then I will be able to receive it. I'll be able to verify that it's come from you, and it will be encrypted, so we kind of have like a secure channel. And then Alice would reply with the same thing. Okay, great. Here's how you can communicate with me. And these identifiers are unique for that relationship. So they kind of end up with this store, which is like kind of like your phone number, like your contact list, but where every single number, you're not giving out the same number to everybody, you're giving out a different number with a different private key, with different, a different key pair and a different communication point. So these relationships can be managed separately, and they can be persistent, or as long as both parties want to engage in it. And then on top of that base layer, which isn't trust, but it's like the means to build trust and to maintain it, you can start to have more complex things built on top. That's what I think, at least, we will start to see. So I think that's it. Yeah, and it's just, like these messages can be verified and decrypted, so that Alice knows, oh, this communication, say, came from Bob, and nobody else was able to read it. Okay, so, we're still experimenting and playing around with this stuff. So currently we've built stuff using the Hyperledger Stack. I personally really like the Hyperledger Stack because they have implemented essentially anonymous credential cryptography. It's a bit old, 2002, still using RSA cryptography, but hopefully they'll push on. And I recognize some people will say, it's not interoperable. There's still some interoperability challenges, and hopefully they will be worked through too. Yeah, so we use Akapi, which is this, it's called an agent developed by British Columbia. An agent is an implementation of Hyperledger Aries RFCs, which is just like, okay, this, if you're going to implement an agent using it follows Hyperledger Aries, you must specify these protocols. So yeah, we just use that. It's open source code. You can go check it out. And we've implemented a controller. So a controller enables you, the developer, to write business logic that uses this functionality. So like, how do I create Titcombe connections with parties? How do I ask them for proofs? How do they ask me for proofs? How do I, present credentials, issue credentials? And I think this is really nice because it's easy, right? Like we've done this part for you, and this part's already done. So now you can start thinking about the business logic you want to implement in your code or however. So there's a really nice playground for you to experiment in. So I just wanted to go into that now because hopefully that was a bit much. So this is our project, PyDensity. It's a repo. I would really say it's like a playground for us. Like we've just been messing around in here. There's the libraries folder, which is kind of like the code, right? This is like the things that we implement so you don't have to. The main library is this Aries basic controller. So the Aries basic controller, you can pip install this now, so you don't even need to care about this too much, but essentially all it's doing is wrapping a Swagger API. So the Swagger API talks to the agent, and says, do this for me. Should have an example of this somewhere. No. Yeah, so this is the Swagger agent API for Agent Bob. And you can send Bob a message saying, hey, Bob, create an invitation for me. And we just basically brought that Swagger API into Python so that you can start, doing that stuff in your code. So, that there's a few other things in here, like the stuff for protocols, the stuff for sending attachments. So, now over Vidcon, we can send files, for example, that are signed or, but really, I wouldn't worry too much about looking into this libs folder unless you really want to dig into the code. But the best folder is probably this tutorials folder. So, you can start with the Aries basic controller, which should take you from, I know nothing about developing, about self-sovereign identity to, hey, I can actually do all of the protocols, at least that Aries supports, and I can think about, rather than having to worry about how this stuff works on the SSI layer, I can think about at the business level, how might this work in my app? Might this work? Maybe it doesn't, but I think at least you can kind of cut through a lot of the complexity and start thinking about, the layer up. Yeah, and just quickly to run this stuff, you'd CD into like, and then it's just use Docker, so /manage up, which will like spin up the tutorial. It follows this Docker compose file, which basically has the agents in there and then the controllers, which are notebooks. So you spin it up, and then you want to, so you typically go for logs, so we can just get this token, which is like, okay, how do I authenticate into the notebook? So it's usually Alice and Bob, but sometimes there's more. So if there's other ones, then you can do Docker PS, and you'll see all of the containers that we've spun up. Okay, so this is a bit much, but and then when you go to, so like you go to localhost 888, which is like Alice, and you'll have a series of tutorials which literally they'll walk you through from, okay, here's some stuff about SSI and like why we chose the Hyperledger Stack. And part 2 is like, okay, now I want to just code this stuff. I want to use your library to do something. This should, understand like, okay, what's going on in this Docker compose file? How do you get started? How do you use the library that we created? What the listeners do? Really, like, it should take you through the whole process. I hope. And if you have any challenges, get in touch. We're still working on these to get them better. But really, it's just so that you can, once you run through all this stuff, you should be able to kind of forget about the PyIdentity repo, pip install the Aries basic controller package, and just, off you go. You can start playing around with Akamai agents and these protocols in whatever, like for single sign-on, like forget about using username and passwords. You can start like thinking about how it's useful to you, not how to actually implement this stuff, like the lower level stuff. Yeah, so I mean, I think that's basically it. I mean, I don't know if it's worth going through one of these, but I really, basically, if you've not used Jupyter, you just go shift enter, you can just run through all these. So that's like saying, okay, this is where my agent kind of lives. This is like how I communicate with it. And I'm saying, okay, just pointing where to send the API requests to. And down here, it's like create invitation. You're just running this, basically this Swagger endpoint. I guess the only other thing to remember is these are typically, so within SSI, the model is, you have an agent, you have a controller, you want to control your agent to do something, but typically your agent is communicating with another agent, right? Like that's the model. We are interacting as peers, so we need to interact with at least one other entity. So, you know, most of our tutorials involve more than one like notebook series, if you like. It's like localhost 8889 and 888 is typically the ones that we use. And these, you know, like these examples, like part 3 will say establishing connection Alice, you know, and make sure you're using Bob's notebook as well so you can play both roles. And then you just have to remember, you know, this is a tutorial, you're playing both roles, but when you're developing at, you know, at production, you only play one role, obviously. You know, you're playing the issuer or the verifier. You want to verify a certain piece of information for within your context. I think that's it. So like, I would definitely, you know, if you're interested in this stuff, this tutorial series should take you all the way to, great, now I kind of understand what the hell he's talking about. And then, you know, the next tutorial to take is this one, like the staging net, which is like, okay, great, now I've played around. Now I can like actually take this stuff out into the wild so that, you know, we can have like a production system, a website that I can go to and start interacting with. Yeah, I think that's it. And so the other thing is we have a series of projects, this is kind of our playground, right? Like before we kind of take a system and say, okay, let's build a production system with like front end, we always create a series of notebooks to like run through the flows. And I think that's kind of a nice place to go to if you've been through this stuff and you're like, oh, I still kind of don't get how it's useful. The projects might give you some ideas of how you might actually, you know, what the business logic might mean, might be useful for you. Cool. That was good. It was a bit rushed. I don't know if there's any questions. If you have time, I can answer some.
So we'll just quickly go into both Opus and PryVote. But before we do, this is just like a picture of the ecosystem which Will was talking about. So we've built an example with 2 projects, Opus and PryVote. And in our system, Opus is the credential issuer and PryVote is the credential verifier. So Opus posts our credential schema to the registry and a credential to the registry. I mean to the DLT, and will issue a credential from this schema to Alice, Bob, or Carol. And then after they have these credentials, they can go along to PryVote and prove membership of a community to allow some privacy preserving voting flow. So for Opus, what we wanted to do was we wanted to do third-party data onboarding as our credential. So what happens is a user will go to Opus and make a connection, and then Opus will issue them with a unique string. And then once this user has posted that unique string to their GitHub account, then Opus will crawl the GitHub URL and then issue off that data as a credential. So to show this sort of process of defining what we want to do, create a series of notebooks to demonstrate each module of that working properly, and then turning that into a service. And we'll just go through these controllers here. So this is the Opus server, and it's our notebook on that side. And what this should sort of look like is this here. So we have our Opus server logic, and that's what's going on here. We have our agent that we're speaking to, and we have our indie network. On the other side, we'll have just, let's say, us demoing a user, Alice, who has her agent, and the Jupyter notebook, which is allowing us to do the server logic for that. Okay, so we can begin this by first defining a schema on the ledger. So at the moment, there aren't any schemas on the ledger. So first we set up our connection with our basic controller. We can then write a schema to the ledger. 2 seconds. And we've lost Tom. We can write a schema to the ledger. We write a credential for that schema to the ledger. And we can see these once they are done over on here. So there is our first, that's our schema. And if we go through to the second page, you see our credential definition being browsed off the ledger, which we're running locally right now. So next we want to put in our application logic. We have our ledger on our credential being registered. Now we want to create or check that we have an active connection with our user agent and set up some listeners to deal with anything that we receive from them. So what we're going to be using here is this message handler to communicate this unique code and the username back and forth. So I'm going to run through the steps over on the user side. So just making sure that we're connected, and we're registering our own set of listeners. So now we're at the stage where we can send across a basic message. But first, we're going to send a unique code over from Opus. It's worth also saying that we're managing this from a manage up sort of scenario, and you can see all our hosts here. So we have this unique string. We post it over here with this message, post Opus to your GitHub profile. And I have done that earlier, and it should be that same string. Maybe not. Yeah, there we go. Ends in 380 and starts with 53. There we go. Okay, so we've received that. We put it onto our GitHub page, and then we send that back. So now we've got this user response haul. So we just do some really basic parsing of the GitHub address with that username. So, yep, we were able to match this string, which I put in my page, with the one we produced earlier. And after that, we go into this section to see which organizations I'm a member of. And if we're a member of the organization, then we carry on. So now we create a credential here, which has my username for GitHub and a true or false value for whether I'm an OpenMined member, based on whether I passed this test. And once that's been done, all I need to do from the Opus side is send a credential. So we've received a credential offer over here. We can double check this with our credential exchange records. And once we've got this valid offer of a credential, we can then actually request the credential itself. You see it's been acknowledged over here. Once we've got the credential, we can store it within our agent. So that's how we built the logic for how this flow works. And we've actually also deployed this at this address. And it would be good if anybody on the chat would want to test it out. That's it from me just now, and then I'll just hand over to Tom, who has returned. Yep, cool. Yep. Stop share.
Okay. Yeah, so I'm going to talk to you today about PryVote. So PryVote is a new project that we've started working on, which is aiming to develop privacy-preserving voting systems. And I know the idea of electronic voting can be a bit contentious to some people. So I just want to clarify what we mean on voting. So yes, I mean, it can apply to voting on national elections, very high stakes things. And while that may be something we'll look into the future, it's not the primary focus at the moment. And voting covers all the way from those very important votes to seemingly trivial things like who gives the best talk at PriCon. Or it could even be voting on statements. Do I agree? Do I disagree with that thing that you just said? But regardless of the vote itself, there are two things that you really need to secure. And that's trust and privacy. If I'm holding a vote on a particular thing, I need to trust that the people who are voting are part of the group, part of the franchise that I've selected. And that's where self-sovereign identity comes into PryVote. So by using credentials of group membership, we can guarantee that somebody is part of has the eligibility to vote without necessarily exposing their real identity. Trust extends to the voters themselves as well. So you need to trust that your vote is being counted and being counted correctly. You also need privacy. So you don't want your vote to be revealed. And in some cases, you don't want the fact that you have voted to be revealed at all. But the levels of trust and the levels of privacy that we need depends quite heavily on the context of the vote. So, for example, most of us probably wouldn't care if our favorite talk of PriCon got released. So perhaps privacy in that context is, doesn't need to be as high. And because of this, with PryVote, we're not trying to just develop a single bit of software that you can use for every single vote. Rather, we're building the kind of framework and the tools that will allow you to develop the voting applications and systems that adapt and scale to whatever the context is. So I've already mentioned SSI, self-sovereign identity, as being a foundational principle of PryVote, but it doesn't stop there. So we're looking at other techniques like functional encryption, secure multi-party computation, differential privacy, and combining these all to create a kind of a secure and private voting system. And so while there are, loads of different types of votes, I'm going to be talking to you today about just a specific protocol that we've been looking at. And this protocol uses secure multi-party computation. A brief summary of what that is. First of all, if you want more information on SMPC, there's a great tutorial on the PySIFT repository for you to check out. But briefly, with SMPC, we encrypt a value and split it into multiple shares. And we give a single share to different parties. And you can't decrypt the value unless you have all of the shares together. The crucial part of SMPC is that you can still perform operations on the individual encrypted shares. So you can give your secret shares, perform an operation, then decrypt it. And you come out with your plain text result that would be the same as if you'd just done the operation on the plain text value. So what is this voting protocol? Well, as a UK citizen, when I go to vote, and this is the same in many countries, I don't actually get to be involved in the vote counting process. I don't see my vote getting counted, but I can trust that it is getting counted because representatives of all of the major parties are present at the vote counting process. And there is no equilibrium where it is advantageous for all of them to lie about what my vote is. So because of that antagonism, I can trust that my vote is being counted correctly. And that's what we're trying to replicate through the secure multi-party voting setting. So we start out with actually verifying that you have the right to vote. So this is the SSI. Bob has a credential that says he's part of OpenMined, for example, which he shows to a third-party mediator. That mediator verifies, the credential verifies that Bob is indeed part of OpenMined and that OpenMined is a valid franchise for this particular vote. And the mediator issues Bob a voter key. This voter key is used to actually send a vote to the vote counters. And you might ask, well, why do we need this intermediary step? Why don't we just go straight from Bob to the vote counters? And it's just adding a layer of abstraction in between the voters and the people who have a stake in the election, just to make it a little more difficult for them to reveal your identity and therefore, protect you from coercion. a little bit better. So once we have this voter key, we actually do the voting. Bob and the other voters, they encrypt their vote and split it into different shares, secret shares. And they give one of these shares to each of the vote counters. These vote counters are acting as the kind of voting parties, the parties of the vote, rather. So in an election, these would be the parties themselves. So remember that there is no reason for all of these different parties to collaborate together. Each one of these vote parties will get votes or secret vote shares from all the voters. And what they do with these, they sum them up together, just as if they were summing up or counting plain text votes. And once the voting's over, it's time to aggregate and find out the result. So each of these vote parties, these vote counters, share their summations of secret shares with all the other parties. Now, once you have all the summations of shares, you can decrypt to get the plain text result of the vote. That's the crucial point. You can get the plain text result, but you can't get the plain text value of any individual vote. So I'll walk you through a demonstration of this. Can you still see my screen, by the way, or am I still showing am I showing the PowerPoint, or am I showing the Jupyter Notebook?
We've got the aggregation phase PowerPoint at this stage.
Okay, one thing then I will reshare. Sorry for the stop and flow. So this is a tutorial, a Jupyter Notebook showing this voting protocol in practice. And this is on the PyDentity repository under the PryVote project. So feel free to check it out and play around with it. This is still in early development, so we've not had time yet to implement SSI to validate the voters. So just for the purposes of this workshop, kind of assume that the voters have been validated and that they have the right to vote. What we're showing here is the secure multi-party computation side of it. So we define the vote, and today we are voting on who has the best workshop of PriCon2020. Is it going to be PryVote, PyDP, or PyVertical? I wonder who we're going to decide wins. Then we define our voter. Our voter has the ability to encrypt their vote into these secret shares. The vote counters in this context would be, you'd have a vote counter representing PryVote, you'd have a vote counter representing PyDP, and one representing PyVertical. And we split our, encrypt and split our vote into a share for PryVote, a share for PyDP, and a share for PyVertical. What we're encrypting here is not the string of PryVote or whatever you want to vote for. We're representing our vote as a one-hot vector. So if you wanted to vote for PryVote, you'd do 100, where the 1 is in the place of PryVote. And what you encrypt is you encrypt each of these 1s and 0s separately. So for this 1, you encrypt and get a set of secret shares. For the 1, you have a set of secret shares for the 0, and you have a set of secret shares for the second 0. As a voter, I send one of my secret shares for each of those 1s and 0s to each of the counters. So the counters then, they receive 3 secret shares, one relating to a PryVote vote, one relating to a PyDP vote, and one relating to a PyVertical vote. And they keep a summation of those 3 shares separately. Our Q is just some SMPC value. We define our voters, and now it's time to actually vote. And we can see in plain text, we've got 3 votes for PryVote, 2 for PyDP, and 2 for PyVertical. So great, PryVote seems like it should have won. If we ask everybody individually, let's just see if the vote counters come to the same conclusion as well. We do the voting. Let's look at what is happening under the hood here. So red is a vote counter. So a party, let's say it's the PryVote vote counter in this case. Let's look at the sums that PryVote is keeping track of during the voting process. And you can see they don't make sense. There's a huge number. We've only got 7 people voting. This shows that the vote counters cannot make sense of the vote as it's happening. They can't understand what any individual is voting, and they can't understand how the vote is going while it's still going on, which is good for us. Privacy, security, great. Now it's time to decrypt the vote. So the voting is finished, and the different vote counters need to share their shares. So we combine them here and we decrypt them using the SMPC protocol, and we get our results. So we have our votes of 3 for PryVote, 2 for PyDP, and 2 for PyVertical. PryVote is the winner, and all the parties agree on it. Great. So just a couple of questions on security. How do I know as a voter that my vote has been counted? Let's say yellow knows that I'm probably likely to vote blue. Why would yellow include my vote? Well, if the summation of shares that yellow holds uses a different subset of people than blue or than red, when you try to decrypt the summation, the combined summation at the end, you will get a nonsensical result. So if the result makes sense, like it does here, 322, that's valid, then you know as a voter, either my vote was included by everybody or it was included by nobody. Now, the being included by nobody, that has practical solutions, such as one of the parties is neutral and has no skin in the game. Therefore, why would they omit anybody from the result? Now, this isn't an infallible process, far from it, but this is just an example of the protocols that we're thinking about and that we're trying to develop at OpenMined to kind of get private and secure voting in a very scalable and useful way. So, I mean, if this interests you and you'd like to shape some voting protocols, then definitely join us. Conversely, if you think this is sacrilegious and is full of security holes, then also join us and fix those holes. So that's a brief run through of PryVote. As I said, it's still in early stages of development. So this space will be moving very fast, very quickly. And on that, I defer back to Adam and Will if they have anything to add.
Yeah, sure. Thanks, Tom. I'm just going to put the IP address of our demo in the chat now. I think we have to finish up in the next couple of minutes, but that's about it. Will?
Questions? We're not have time for questions.
Do we have any questions?
Hopefully our demo doesn't crash.
Yeah, well, let's get out of here before it does.
DDS.
So it looks like we've had time for all the questions. Yeah, on that note, please come and join us if this stuff is interesting. And yeah, we look forward to seeing you on the Slack. Cheers.